Hello. So we're gonna start our seminar. Announcements. Please do the click to tell Joanna and me you were here. So about 10 of you forgot to do that last week. So you can have QR code at the back or a QR code on the front. Go ahead and do it. So today I have the pleasure. We have the pleasure of having Dr. Kanok Boriboonsomsin. So you have for me to pronounce the last name. Kanok is a research engineer in the transportation group at the CE-CERT, the Center for Environmental Research and Technology at the University of Riverside. And Kanok is an expert in transport modeling, freight modeling, emissions modeling, air quality, testing of vehicles, and many other aspects of transportation research. And today, we're going to learn about charging for medium and heavy duty vehicles. So, thanks again for coming, and we're all yours.
Great. Thank you, Miguel, and good afternoon, everyone. It's my pleasure to be here. I was here at UC Davis maybe almost 20 years ago, so it's very nice to be back and see the beautiful campus in a beautiful day like this. Today, I'm going to talk about charging scenario for medium and heavy duty electric trucks. And before I get started on the seminar, I just want to introduce where I'm from a little bit. So I'm with College of Engineering Center for Environmental Research and Technology. We are the largest research center on UC Riverside campus. We are under the College of Engineering, but we are off campus. And our mission involves doing good research and educating students, and then also serve public by disseminating our research results for good causes. At CE-CERT, we have 5 research areas. The first one is renewable energy production and integration. We have a group that does a lot of solar. We have in that group, they also look at integrating hydrogen and all that for transportation purposes. We also have transportation system, the group that I'm affiliated with. We look at transportation as a whole, from the vehicle aspect as well as the interaction of vehicles with transportation infrastructure. We have a group that does a lot of emissions testing and look at the impact of different fields on vehicle emissions. We also have a group that kind of try to understand how emissions from the vehicles, once released into the atmosphere, how they form, how they interact with other chemicals in the air and create different air pollution. And lastly, we have a relatively researched area in the human exposure and health effect. Okay, for today's seminar though, I will again focus specifically on charging electric truck. And I will first kind of go through some background information and motivation. And then I will talk about some real world data that we have observed from the early adopters of electric trucks. And then we will go into the assessment of charging scenarios for fleets that want to electrify in the future. And then there will be some concluding remarks at the end. Okay, I think most of you are aware that the governor set goals, ambitious goals for the state a couple of years ago. And it touched on many aspects of our transportation system. And one of those goals is to transition fully our short-haul or drayage fleets to zero-emission vehicles by 2035. And the main regulation that will do that will help us get there, is advanced clean fleet. Right now, there are uncertainties around that regulation, but that's not the topic of today's discussion. But because of this goal, many fleets, truck fleets, we have to start thinking about how they're going to do that, how they're going to become 100% electric fleet in the next decade. Now, any of you own an electric truck? No? Okay, maybe not yet. Maybe after this talk, you may be inspired into owning one. How about any of you own an EV, electric car? Okay. Where do you charge your electric car?
At my apartment complex,
Okay,
that's pretty much it.
I see. Anyone charge it here too when you come to work?
Yeah.
Okay.
The chargers are full all the time.
Okay. Yeah. So yeah, if you own electric car, and like most people, they will charge at home or apartment complex. And when they go to work, sometimes they charge it at work. Maybe they can also charge it when you go to shopping, if that shopping center has charging options for you. Now, for electric truck fleet, though, it's more complex, right? Because they don't work at the same location every day, right? They have to deliver goods to different customers. So it's harder for them to kind of plan their charging. So when a fleet wants to electrify and transition their trucks into electric trucks, they have to think about a lot of things. At the strategic level, they have to think about, okay, what are my goals? How much of my fleet can I electrify? On what timeline? Maybe half of the fleet by certain years and then the other half by another year. And then what would be my fleet composition? Do I get like all the same electric truck across my fleet? Do I need one that maybe have a longer range than the others? And things like that. The next thing is charging infrastructure investment. If I'm gonna have electric trucks, what do I do with charging infrastructure? How many charging stations do I need at my home base, in my yard? Or would I rely on some public charging options? And then when they think about charging infrastructure, then they have to think further about the grid at their site, right? Is the grid in my yard ready to put in certain amount of charging stations? And these are something that they have to think 1 or 2 years ahead of time, right? These are a very strategic level. The next level is the tactical level. So these questions are perhaps in the months leading up to the actual implementation. Things like route planning. Some customers may be far away from the yard that electric truck may not work. And then in that case, they have to identify perhaps public charging station that may be available on route. And then once they do that, then they have to think about, okay, how do I schedule? Because I have to get to my customer by a certain time window. But if I have to stop to charge the truck, how do I fit that into the truck schedule? And then because electric trucks use battery, they also have to think about how to manage the charging in a way that preserves battery health. And lastly, at the operational level, this is on a day-to-day basis, right? It comes down to the day of operation, how to decide the dispatching and schedule which customer to visit first. And then along the way, does the truck have to stop at a charging station to get charged before going to the next customer? And then if the truck gets delayed, gets stuck in traffic, and then the state of charge drop below what it should be, then that real-time decision needs to happen. Maybe we route the truck to the charging station first before making the next stop. And then along the way, using telematic system to monitor the energy consumption of the truck in real time, state of charge, state of health of the battery, and even the availability of charging station, right? And use those real-time information in the optimization of the operation for that day. Last but not least, driver. Driver is very important because driving behavior accounts for about 30% of variation in energy consumption of any vehicles. So they have to think about training the driver to be able to maximize the efficiency of electric trucks. Okay, so there are many electric truck models in the market now commercially available. These are some examples only. And these are from 3 different manufacturers, and they have different ranges from just 150 miles to 275 miles, which is already impressive if you think about how heavy this thing is. And of course, the longer driving range require a larger battery size. And another aspect that is not talked about as much is the maximum charging rate that the truck can receive. Because if you have a 350 kilowatt ultra fast charger, but your truck can only receive 150 kilowatt maximum, then it doesn't make any, it doesn't help, right? Your truck can only receive that much. So the charging time will still be long. But if you have a higher maximum charging rate, that allows your truck to be charged faster. Now, in terms of infrastructure, the most common one that we see is DC fast chargers. For electric trucks, maybe the one that is 50 kilowatt probably not going to cut it. We probably want to think about 150 or faster power level. And there are also wireless charging system that has been demonstrated that can allow charging up to 500 kilowatt. And this wireless charging system is going to be handy in tight space, for example, at loading dock. So you can just put one at the loading dock and allow the truck to be charged when it's stopped there for loading or unloading. And then in the work right now, there are many efforts to try to develop megawatt charging system that can provide 1, 2, 3 megawatt of charging power, very strong and fast. But that's not something that is available just yet. Okay, so we know about the trucks, we know about what are available charging infrastructure options. Now we're going to talk a little bit about charging locations, because as a fleet owner, you probably will think about trying to charge your trucks at your home base first. And that's very low-hanging fruit, right? However, with new chargers and technology, you can also potentially charge your truck at any stop that it makes, right? Whether it be at the port, whether it be at the customer locations, because in a day of a truck driver, it go from your home base, it start the day at your home base. It go to, let's say, go to the port to pick up container. Maybe it has to wait at the port for about 1 hour, waiting in line just to get into the port to pick up that container. And then it go and drop off container at a customer location. And that take about 30 minutes to do that. So every stop along the way, that 30 minutes, that 20 minutes, you can take that opportunity to also charge the truck, because the truck is there already, right? You're not losing any extra time for that. And then the other option is network charging. And by network, I'm referring to charging station networks. And that can be public, right? Anyone can use it, or it can be a private setting, just like Tesla supercharger network, right? So only certain type of trucks from certain OEMs, or it's based on subscription. But the general idea is these charging stations could be available along the route. And then if you need to, then you can take a trip to get to that charging station in order to get charged, just like going to a gas station to fill up your car. Now, right now, most of the charging infrastructure investment go into what is called centralized charging. So we try to develop charging station that can accommodate many trucks at the same location. Just think about truck centers, right? That right now pump gas, but yeah, to turn that into charging station for trucks. And that model is good because it can accommodate many truck charging at the same time. The limitation might be that when you have a congregation of many trucks that charge at the same time, it's gonna create a huge charging load requirement, right? So in this graphic, 50 of these big trucks charging together will require the charging load that is this amount about the same as the entire state, Empire State Building. So that means you may need to upgrade your grid to be able to provide that much power. And it's gonna take a long time to get there. So is there a way that we can maybe look at distribute the charging both spatially and temporally in a way that try to bring down the load requirement and utilize what is already available on our grid today? So that's the motivation of this research. Now, before we get into that part of the seminar, I will go through a few slides on what early adopters of electric trucks did in terms of utilizing the electric trucks. This part of the research, we use data from real fleets that adopt electric trucks from Volvo. And there are 8 fleets that together use 15 electric trucks in their operations. There are 2 classes of trucks. Class 7 is a little small. Class 7 is a little smaller. And that's why it can go farther, having a range of 150 miles. And then Class 8 is the largest truck that you can find on the road. And it has OEM estimated range of 120 miles. So in this table, as well as the following tables, as well as the ones in the following slides, fleets are color coded. So if you see rows with the same color, that means those trucks are from the same fleet. Now, this table looks a little busy, but I would like to just highlight a few things. Again, the data that go into this table is real-world data from the actual operation of the different fleets. And we have data for almost all of them. We have data for over 2 years. So it's very representative of how they operate these trucks. And what is interesting is when we look at the actual energy consumption of this truck and compare that to what the OEM advertise, right? They come very close to the advertised numbers. For example, for Class 7, the advertised range is 150 miles, and the real world number that we observed is 141 miles. So that's a good thing. And for Class 8, the advertised number is 120 miles, and the real world number is 124, even closer. And this is helpful because it gives confidence to the fleet that what they're gonna get in the real world is close to what the OEM advertised, right? So that way they can plan their operation with the confidence that the truck will be able to do what it was advertised to do. Now, in this table, again, I will just highlight a few things that are interesting. The first thing is number of charging session tour. And by tour, what I mean is when you have a truck that go out to a customer that is considered one trip, right? And then it go to the next customer and next customer. Each of those is considered a trip. But then when it come back to the home base, that series of trip is considered as one tour. And so when we see the average number of charging sessions per tour kind of being around one, that means for most of these trucks, they are charged only once a day, right? So they go and do their things, they come back, they get plugged in and left overnight or whatnot, and then until the next day, they go out and repeat that. Another thing that is interesting is the percent of charging sessions that occur off-site, and it's very small, mostly less than 5%. And that's not surprising because this data was from 2021, 22, and back then there were not a lot of charging options that are publicly available. So most of the time, the trucks were charged at their home base. Now, when we look at the variation in truck operations, again, there are many plots, but let's go through them one by one. The first one is average trip distance. And if you remember, the range of the truck is about 120 miles for Class 8 and 150 miles for Class 7. And the trip distance that we see is well below 20 miles, right? So these are mostly used for short trips. And that's somewhat expected because fleets are still getting used to what the trucks can do. So they tended to be a little bit conservative at the beginning. They don't want to leave their trucks stranded on the road. So they use for short trip. And then when we look at the longest trip distance, again, yeah, they never exceed what the range would be. And that makes sense, right? Because it's not doable anyway. The next one to look at is the longest tour distance. So we see that there are a couple cases where the truck actually took a longer distance than it can before it can come back to the home base. And these are instances where these trucks had off-site charging that allow it to actually go further beyond its estimated driving range before come back to the home base. Now, this is another BC graphic. It shows charging activity by time of day for each of the trucks. And on this column, it's just time of day, right? And then these are all the different trucks. What we observe is all over the place. Not every truck is charged or plugged in at the same time of the day. So before we see the real world data, one of the things that people were concerned about is if we have a large amount of electric trucks plugged into the chargers at the same time throughout the region, what would happen to the peak load, right, for the electricity grid? Because even 50 trucks will generate a lot of peak load already from the previous slide that we see. What if 2,000 trucks plugged in at the same time? That will make it even worse, right? But from the real world data that we observe, it turns out that not every fleet operates the same way. Some actually operate during the nighttime, which means the truck come back and plug in the morning and then charge throughout the daytime. So this one is the one that charge during the nighttime, right? The traditional model, 9 to 5 operation and then plug in and charge over the night. But these trucks is opposite. They operate during the nighttime and then they plug in and get charged during the daytime. And then there are some trucks that their operation vary and they charge and throughout the day, depending on when they are back to the home base. This is good news because collectively, basically, they distribute the charging load throughout the day. Now, another thing that we look at, and this is a little bit deviate from the charging aspect that we are talking about today, but I just want to have this sidebar. So one of the main issues associated with heavy-duty truck is that these diesel vehicles produce a lot of emissions, especially nitrogen oxides and particulates. And because they go to freight hubs that are surrounded by communities, so many communities are heavily impacted by diesel emissions from these trucks. So what we look at is, what if we can transition this truck from diesel to zero emissions, such as electric, right? What does it mean for the communities nearby? So we use the data that we have and look at the operation footprint of each truck and see how much time or how much distance they operate inside these, what is called disadvantaged communities. And we found that it varies depending on where they are based at, where their customers are, and then the route that they took, right? But overall, on average, about 50% of the time, these trucks operate inside or around disadvantaged communities. That means right away, if we can deploy zero emission trucks, there will be a lot of emission reduction benefits and air quality benefits for these communities. Okay, so for this part of the work, there are a few observations. One is that, again, the fleets that are early adopters, initially they were conservative with how they use these new technologies. So they use the trucks mostly within the driving range of the trucks. But in the future, once there is more public charging infrastructure available, the fleet can expand the use of this truck, right, to perhaps farther locations without having to worry about running out of batteries. Another thing, again, which is surprising, is the real world data show us that not every fleet and every trucks are charged at the same time. And the fact that they have that different charging schedule allow the total charging load to be distributed throughout the day. And then lastly, at least for the trucks in this data set, operate about 50% of their time and distance in disadvantaged community that could result in a significant reduction in emission benefit. Okay, I will pause here for now for this first part of the seminar and see if anyone has any question.
The fleet that you introduced, I assume that they are belong to the different operators, yes? So do they do the same businesses, this fleet operator, for example, maybe some of them do the specific type of the businesses, and because of that, they have a different charging time, or they have all of them have the same business style?
Oh, they are all different. Yeah, good question. So even though they fall into a broad classification of what is called regional distribution,
Oh, okay.
but they serve different types of customer and carry different types of goods.
So maybe it's because of that that they have the different charging type, the charging profiles.
Right, yeah.
Okay.
And that's a good thing because when we think about trucks, sometimes we think that they're all the same, but in fact, in reality, they are so diverse.
Mm.
The type, the size, and the operation or location.
But even when the, for example, the penetration of the heavy duty, electric heavy duty increase, maybe they have some overlap for the charging profile because then the number of the EVs, the heavy duty increase, and then we have the same charging profiles. The case for that.
Yeah, hopefully it will scale up,
Mm.
right? The different profile will scale up depending on the penetration rate of
Mhm.
electric trucks
Right.
and still balance out throughout the day. I see.
Yeah, so you now said that it's all local delivery that you looked into. Is it just because trucks are at the moment only used for local delivery, or did you especially select all of the data set you had only the local?
Yeah, in this, so it's a partnership between Volvo and some of their existing customers. And these are the customers that operate within the driving range of the trucks at the time, the capability of the truck at the time. So it's somewhat self-selected.
You mentioned something about scheduling for charging stations. I want to know that there is some time slot that you want to assign those time slot to trucks for charging, and if there is something like this, do you consider something like walking trucks without any plan to join the line for charging? Do we consider this in our scheduling? And also for charging scheduling, if you have some uncertainty about our model, what is those parameters? For example, how you select what parameters of charging scheduling can be uncertain variables. Yeah.
Okay, so the first question has to do with how we might be able to create a reservation system for charging. I think that's very doable. Perhaps there are some real world example in the electric car space already. But yeah, in theory, if you have a lot of trucks that want to get charged and it create congestion at the charging station and create a queue, perhaps some sort of reservation system could help, right? And then the second question is the uncertainty around charging schedule. There are many uncertainties, especially if you charge off-site. One is travel time, because when you go and try to get to the next destination, the traffic condition may vary, and that will create uncertainty in when you arrive at the charging station, especially if you reserve a spot, right, a time slot for that. And then there is also uncertainty related to energy consumption, because the energy consumption can vary a lot depending on driving condition, like when you're stuck in traffic or when you use a lot of AC, and if the temperature outside is hot and things like that, right? These are all factors that can impact real world energy consumption of the truck, which means your state of charge may get below what you want sooner than your scheduled charging session. So, and then when you arrive there, if you don't have reservation, again, you have to get in the queue, and that create another uncertainty in the schedule.
I have a question. When you, in your research, when you say that if the purpose is to remove the trucks and introduce EV trucks, do you consider like the final destination of the old trucks? Like what to do? Like, because you can remove from one place, but maybe they will stay another. I don't know.
Yeah, yes. So we heard that for certain application. So the general life of a truck is start out in a long haul application when it's brand new, because it has to travel a lot of miles per year. And once it gets older, then it gets sold to a regional or drayage application, because those applications require fewer miles per day and more tolerant to break down. Right? And then once it gets super old,
Mhm.
then it gets sold to other countries.
Oh.
Yes.
Okay, so I was wondering for the average of 50% operation in disadvantaged communities, whether this is just the fact that they're on freeways and disadvantaged communities are often along freeways, or if this is like related to Amazon warehouses and these are the trucks that are distributing goods from the warehouses.
Yeah, it's a mix of everything depending on where the home base of the truck is itself, because if it's located inside disadvantaged community, then it start off its day having to pass through these communities.
Okay.
But it also depends on where their customer are. If their customer are mostly in non-disadvantaged communities, then yeah, they may not spend as much time, right? And then yeah, the route that they take, because like this truck, it takes that freeway a lot, and that freeway is not next to any disadvantaged community.
Okay.
Yes.
So again, following up on this, so did you look into how many of these trucks receive the HVIP incentive? Because one condition, I mean, HVIP provides more incentive to trucks operating in disadvantaged communities. So was that a result of receiving those incentives?
I'm not sure if this truck were part of HVIP or receive HVIP incentive, but yeah, I acknowledge that for HVIP, yeah, there's requirement for the recipient to track how much of their operation actually occurred inside disadvantaged community.
I have a couple of more questions. So how are these data recorded?
This one was actually recorded by the OEM themselves using telematics, and then they share with us.
Okay, and was the data on payload ever recorded? Because that also affects the range, and when you compare that to the manufacturer advertised range, manufacturers usually advertise like fully loaded truck range. And if this also includes like truck trips with like zero load, then it may not be as impressive as we might think.
Right, yeah, that's good point. We don't have the payload data. And that is something that is hard to get. But yeah, I agree with your point, because in the real world, not every single trip will be fully loaded.
Thank you.
I have two questions related. Did you get state of charge data on your data set, and did you see any patterns of how they were charging? So that's one, if you had that, and then related to it, for the offside, do you know if those were kind of top off or were they fully charging the battery? What?
Yeah, on the first question, I don't think I have a graphic for that. So we received the state of charge data, and it varied by truck, but most of the time, the operator just plug the truck as soon as it come back at the home base. It doesn't matter what the state of charge is. Yeah, because sometimes we see that even it come back at 40%, it got plugged in right away. And the second question,
For the offside.
for the offside, yeah, back then, actually, there were not public charging station. The offsite location in this data set is actually a truck dealer of that OEM. Okay.
I think we had one question online. John, can you unmute yourself?
You can unmute yourself and ask the question.
Maybe they can.
Okay, we will get back to you. Okay, last question.
Yeah, maybe one last question. So you talked about the different types of charging, like home-based charging, opportunity charging, third one, I don't know what it's called. For the opportunity charging, you would need information about how long the vehicle is standing at certain locations. Is this included in the telematics data, everything like this? So you talked about being at the port, waiting for an hour or stuff like this. This is all in the data.
Yeah, so the telematic data doesn't quantify that for you, but using that data, you can derive that information. And in terms of terminology, yeah, I call the last type I call it network charging because some others call it on-route charging, but what we see in the data is that sometimes it's not really on-route, but the driver will have to get out of his way to get to that charging station because otherwise the truck gonna run out of battery. So yeah, then we call it network charging for now. There may be better terms. If you have any ideas, I'm open to suggestion. Okay, we're gonna get into the second part of the seminar, which is the assessment of electric truck charging scenarios. So in the first part, we use data from the actual electric truck to observe how they were used and all that. Now, in the second part, to be able to assess for the fleets that have not electrified, right, how they may be able to think about charging their truck. And to do that, we have to use data from the diesel trucks that they have now, right? Because diesel trucks can go 1,000 miles without any problem, things like that. So we have to understand how the fleet actually operate their truck now. And if those trucks are turned into electric truck, how they may have to change operation and how they can charge those trucks. So we use a different data set for this. And again, it's real world operation of the different fleets, but from their diesel trucks. We have 3 different applications. One is drayage, the ones that kind of haul containers from the port or to the port and customer location. And in this case, yeah, we can see that there's a lot of activity around the ports of Los Angeles and Long Beach. Occasionally, they may have to go out of their way to the Inland Empire, which is close to Riverside. But most of the time, they just spend their time mostly around the port. The second type of fleet is beverage distribution. So they are based out of downtown Los Angeles, and they distribute beers and liquor and drinks to retail stores in LA. Last one is food distribution. This is grocery truck. They are based out here in Riverside actually, and they serve their grocery location throughout not just LA, but almost like throughout Southern California. So 3 different applications with unique different patterns. Now, because these are diesel trucks, right? So for us to be able to assess how they can be charged if they become electric trucks, we have to be able to understand how much energy that operation gonna require if the truck is electric. So we have to be able to model electric truck energy consumption and charging needs for each of these trucks in our study. And to model that, there are 2 general approaches. One is the top pathway, which is microscopic modeling approach. And for this approach, again, it's better if you have real world data. And the type of real world data that is required for this approach is high resolution data of speed profile, right? Almost like second by second data of driving speed. And if you have information about the road grade that the truck travel on and the way that it carry, that even better, right? Make the results more realistic. And using that data, you need to use powertrain model that will produce estimate of second by second energy consumption associated with all these inputs. And once you know the second by second energy consumption for any trip, then you can estimate what would be the battery state of charge at any point in time. Again, it's data intense because you need that detailed information, but you also produce more accurate estimate of energy consumption. The other approach is called mesoscopic approach. This is where you may not have that level of second by second data to be able to utilize the accurate powertrain model. So you try to use statistical model and reduce the number of inputs and the fidelity of that inputs required. So in this case, if you know just the average speed that the truck was driving at on a link by link basis, and again, if you know the road grade and the way that it carry, those are enough for you to do a reasonable job at estimating how much energy would be required to complete the trip. And then you can estimate battery state of charge. In this study, we use the microscopic approach because the data set that we had collected earlier actually is second by second data. And because of that, I'm going to talk a little bit about the powertrain model that we use. And it's based on basic physics, right? So you have to estimate the power that is required to move the truck forward by overcoming the air drag and the rolling resistance. And once you estimate that power on a second by second basis, then you can look at the energy flow in and out of battery. So if you are in motion, if the truck is in motion, it's going to consume the power that is proportional, it's going to consume the energy that is proportional to the tractive power requirement calculated in the previous slide. And if you turn on AC, then there will be some energy consumption associated with that, right? On the other hand, because electric trucks are equipped with regen braking, so you are actually able to capture some energy back from braking regeneration. And lastly, of course, once the truck is charged, then the battery will receive energy from the charging. And putting all these together, you will get the second by second energy consumption associated with each operation. Now, the next part is identify off-site charging location aside from the home base. So the home base is easy, right? We know where the truck is at the end of its operation, but where else we might want to place a charging station for the trucks. So using the same data set, because it's a detailed second by second operation of the truck, we know how long the truck stopped at each location outside of the home base, whether it be warehouses, whether it be at rail yard or at the port. So we can aggregate the amount of time that it stopped at any locations outside of the home base. And putting all those stop duration information together, then we can rank and sort, right? Where are the top 10 off-site location that my truck stopped at? For example, for the drayage fleet here, the home base is right there, the black dot. And then top 10 location is just close by, right? Inside the ports, picking up container, and maybe a few outside. These are where the warehouses that they visit to drop off container and things like that. Same thing for beverage distribution fleet. Of course, the pattern and the location will be different, but you get the idea. So for each fleet, you can identify top 10, top 20 locations where your trucks visit the most. And those are probably where you want to place a charging station. Maybe you want to talk to the owner of that location. Can I put in some charging station here so that my truck can be charged while serving you while stop at your location? Now, that is specific for your operation, right? Those are the locations where your trucks stop the most. But when we think about network charging, if you are an agency or you are an investor and you want to develop charging station for trucks, you don't just use data from one fleet, right? You have to use data from all the fleets, all the trucks in the region, and try to identify the best location in terms of the most visit, the most stop, and all that, right? And that's where the data from the large scale activity data from a company called Geotab came in. So Geotab is a telematic provider that install telematic device on commercial vehicles to help them track their vehicles and monitor other information about their vehicles. They have a large presence in North America, so they get data from a large number of trucks operating in the US. And they aggregate the data together and be able to provide a lot of insights about truck activity in any region. I should note that this doesn't represent the entire truck population. It's still a sample, but this is probably one of the largest truck samples that I have seen. So we purchased data from Geotab for 3 counties in Southern California and analyzed the data to identify, again, top locations where there's a lot of congregation of trucks and where they also spend a lot of time at. So here we separate into classes, heavy duty and medium duty, because these 2 classes of truck, they serve different applications and their top stop locations may be different. So I show here the top 30 locations for heavy duty vehicles based on the Geotab data. As you can see, they are located along, this is the I-710 corridor that connect between the ports of Los Angeles and Long Beach and downtown LA. So yeah, many of them are actually located along this corridor, and that's not surprising because this is a very major freight corridor in California. Now for medium duty vehicles, it's totally different, right? It's all over the place. It's not focused on specific corridor, and that might be because it align more with land use, right? Where the customer of these trucks are located as opposed to just port and rail yard. And this is Los Angeles Airport, so maybe there's a lot of delivery of food, beverages, uniform to serve businesses at the airport, things like that. Okay, now if you combine the 2 set of stop locations for heavy duty and for medium duty, then we have a combined list that we can use in our next step of analysis. Okay, now I'm going to get into the simulation of charging scenarios. So the 2 pieces are in place. We have ability to estimate energy consumption and battery state of charge of trucks, electric trucks at any point in time. We know where potential charging location might be in terms of for opportunity charging as well as for network charging. So now we're going to simulate all together.
the geotab data, what else do you have except from this destination? Do you have distance, travel distance and so on, or just
For geotab data, you can extract a variety of information, body pattern, trip statistic, and things like that.
Okay.
Okay, for any simulation, yeah, we have to make assumptions, right? And here are the assumptions that we made. On the truck side, we select one of the 3 models that are commercially available. And it's the one that has 150 miles range with 150 kilowatt max charging rate. And because we don't know the weight of the truck for all the trips, we have to assume that it carry a cargo weight of, it has a combined weight of 55,000 pounds. And that number is the average between empty versus fully loaded, right? So we assume a value in the middle. And then on the charging infrastructure side, because the truck has a maximum charging rate of 150 kilowatt, we then assume that every charger, either at the home base or off-site, also has 150 kilowatt max rate. Now, that 150 kilowatt is the maximum charging rate, but in reality, the amount of charging you get depending on the state of charge of the battery as well, as shown in this curve. So many of you may know this already, like when you are low on battery, like your phone, it charge slow at the beginning and then get faster. And then there is an optimal state of charge where your phone seems to charge really, really fast. And then once it's almost full, then the charging speed kind of drop again. The same with the battery in EVs, including electric trucks. Now, other assumptions that were made include that, yeah, we start our simulation where the first trip is assumed to have 100% battery. And then when electric trucks come back to the home base, we assume that they are plugged in right away, just as what we see in the real world data from the first part of the seminar. Here are some interesting assumptions regarding network charging. Because again, network charging is somewhere that may not be on the route, right? Maybe the truck will have to kind of make extra trip or get out of its way to get to that network charging station. So what we assume is that the truck will have to start looking for a network charging station as soon as the state of charge drops to 20%. And then once it gets to that network charging station, it will charge until it has enough battery to get to the next stop with 20% state of charge remaining. Okay. Otherwise, it wouldn't be, without this assumption, that it wouldn't be able to complete the operation. Okay, I'm going to go through a number of tables that show the results. And again, I will only highlight a few things in each table. The first one is for trip distance, is not surprising, right? Based on the map of footprint that we saw earlier, that average trip distance for drayage is fairly short, 13 miles. For beverage distribution is even shorter because it goes from one retailer to another retailer within the city. The food distribution is taking longer trip because it's cover a larger area of the region. And when we look at the tour distance though, for drayage, each tour is about 63 miles. And keep in mind, the assumption is that the range of the truck is 150, right? So 63 miles is just about half of that, less than half. For beverage distribution, it's even shorter, just 28 miles. Now for the food distribution though, is 161 miles, which is already above the driving range. So in that fleet, we have to think about off-site and network charging in order to be able to actually do a lot of the routes that they normally do. Now, in terms of stop, this is quite interesting because when we count number of stops that the truck makes altogether, if we just focus on the drayage, right? Altogether, they make 1,500 stops, and only a quarter of those stops are at the home base. So again, that kind of point to the potential of maybe providing charging at outside location. In fact, if you take the home base and then add top 10 location, outside location to that, it accounts for almost half of the total number of stops. And if you add 10 more outside location, it increased that fraction to 62%. Now, the difference is when it stopped at the home base, each stop average out about 8 hours. So comparable to like overnight, right? It finished the operation for that day. It stopped at the home base for 8 hours until the next day. But the average stop duration at outside location is still quite a lot, right? 3 hours. So those 3 hours could have been used to charge the truck. Here we look at the fraction of tours that would not be possible with electric trucks for the different types of operation. And again, let's just focus on the drayage. So if you only provide home-based charging only, about 13% of the current tours that are being done by diesel trucks would not be possible. Now, if you add 10 off-site locations, that 13% drop to 9%. If you add another 10, it just dropped a little bit to 8%. Now, this is probably unrealistic to assume that at every single off-site location, which are 163 locations, would have some sort of charging availability. But yeah, that would bring the invisible tour down to 4%. On the other hand, perhaps let's combine home-based top 10 or 20 off-site location and also utilize network charging stations when needed. And again, yeah, you can bring down the fraction of invisible tours to 4% with that option. Okay, so this table shows the average charging energy that is received by the truck at different locations in different scenarios. Of course, when you have only home-based charging, all the energy will be received there, right? And and if we again focus on just drayage, so about 167 kilowatt hour will be received at the home base. Now, if we add operating charging, what happens is it takes some of the charging from the home base to outside locations. That's therefore reduce the amount of energy that will be required at the home base, right? And then it shifts that energy to those offsite locations. This table looks at the impact of the detours of network charging. As mentioned earlier, sometimes when the truck has 20% battery, then it has to start looking for network charging station, which may or may not be on the route that is on, right? So if it has to make detours in order to get to the station, what are the impacts? So again, if you focus on the drayage, perhaps what is most interesting is the extra distance and the extra time that would take to get there and then get back on route. So average distance is about a mile extra, and then you will add 4 minutes to that. Now, for those extra trips, it also consumes energy by itself, right? So 7 kilowatt hour just to get to the charging station and back. And yeah, you will spend about an hour at that charging station because you are so low on your battery. And that will make you late to the next stop, right? Because now you spend an hour at the charging station unplanned. The next two slides will look at the charging load, impact on the charging load at the home base. So again, at the home base, we still provide charging station there. And when the truck come back to the home base and they are plugged in, they will create a charging demand, right? And when multiple trucks plug in at the same time, those charging demand are added up. And what happened is, again, if you look at the drayage, we have data for 117 days. And we look at the charging load profile of all those days. And look at the average, which is the blue line, and the max, which is the red line. And the max is not just a single day, it's the max of any day within that period, right? So it's always the maximum combined from all the 117 days. Now, we're going to compare the different scenarios and how the charging load profiles at the home base change when we provide off-site charging and utilizing network charging. So if you only use home-based charging, it's this blue line, right? The charging load at the home base will be quite high because all the trucks will come and charge here with a low battery, so they require a lot of energy at the home base. But if we add 10 off-site locations, top 10 off-site locations, and perhaps also utilize network charging, we see that we can bring the charging load down, right, from about 110, 115 kilowatt on average down to about 95, 100. So that will reduce the amount of energy required at the home base. On top of that, it can help reduce the max power or the peak load for certain times of day, which can help reduce the peak charging. And that can benefit the fleets because then they don't have to build they don't have to install as large the transmission line, the distribution line, and as well as pay the high tariff of the peak charging. And last thing in terms of result is to look at, okay, what if we use different trucks? What are the impact and what are the trade-offs? So all the results previously are for the Kenworth truck, which is 150 miles range. Now, if the fleet decide to use different truck models with longer range, what are the impacts on the number of invisible tours? So one thing to look at is, for example, if you want to use home base only, then we probably need to use trucks that can travel long distance, right? Have longer range. However, if the fleet also willing to utilize off-site charging and network charging in combination, they may not need a truck that has as big battery size. So they can still achieve the same amount of tours that are feasible with electric truck by utilizing more charging options. All right, just to wrap it up. So the first thing is we see from the simulation results that operating charging offer many benefits, right? So it can enable the truck to serve longer routes than its driving range allows. And it can bring down the charging demand and peak charging load at the home base. Now, when it comes to network charging, there are pros and cons. So there are trade-offs there. Even though the utilization of network charging can allow the truck to serve even longer route, right, go further. But it may induce extra time and distance if the charging stations are away from the route that is on. And those are induced VMT that we are trying to reduce as a whole, right? And lastly, the operating and network charging can allow battery size required for the truck to be smaller. And that can mean a lot of things, right? If the truck can use smaller battery size, that potentially reduce the critical minerals required for the battery. And when you have smaller size battery, that means the vehicle could be cheaper. And when you have smaller battery, the weight of the battery will be lighter, which means less pavement damage. However, the use of smaller battery size will have to be weighed against the cost impact, right? Because then you have to invest in more charging location. Okay. And yep, so yeah, all these research are supported by Department of Energy and Center for Advancing Research in Transportation, Emission, Energy, and Health. So I want to acknowledge those. There are many contributors, my staff, as well as current and former PhD students that help put a lot of this together. And I also want to thank many collaborators that make this possible. All right.
For questions, I would like to give a little bit priority to the people online. So you can read some of the questions, please.
Yeah, still currently, I think everyone's still writing Q&A questions.
Okay, so if they're still writing, then you can ask questions now.
Yeah, so when you were talking about the detours that trucks would have to do to reach the network charging opportunities, you just showed the absolute numbers, like I have to make a detour of 1 kilometer. What is it like in comparison to the tour distance I have in total? So what percentage would it be? So this
It's small for drayage. The average tour distance is 60-something miles. So a detour of 1 mile is not a big deal, right? But it's still something compared to operating charging, where you don't have to have that extra distance and time. Yeah, true. Yeah. Okay.
Question online. For different scenarios, if the fleets are composed from different trucks, some are light duty trucks, some are heavy duty trucks, how is the impact on the results?
That's a good question. We haven't looked into that. But when you say light duty, so I presume cars, right? Electric cars, or
This from someone online.
oh, okay, yeah,
Probably the mix of.
Yeah.
A mix, maybe even category 7 and 8.
right, yeah. So I think maybe the charging infrastructure may have to be designed for different classes of vehicles, and the use case may be different too. So yeah, but that's a good point. Yeah, we haven't looked into that.
Another person asked if the slides will be able to download online.
The video will, they can be able to see the video. Quick question for the charging profile. Did you consider any constraints at the depot?
Very good question. The answer is not yet. So, yeah, I have another set of plots just like this that show charging profile at outside locations. And what it does is it shifts the load profile from home base to some of the outside locations. Now, for both types of locations though, we can put constraint on what would be the maximum peak load that is possible. And that means the charging will take longer. But yeah, we have not done that yet.
Another person asked, how are you using this data to help plot out the quantity and type of EV charging systems required at the fleet's distribution/operation centers to enable more EV deployment?
Right. So these are just sample data. Very small number of trucks. But let's say if a fleet is interested in transitioning to 100% electric fleet, and because the fleet will likely already have the operation data of the vehicles, either at the microscopic level or even with the mesoscopic level, if they have data from telematics. This simulation can be done using their real-world data, and that will allow them to kind of generate the results like this specifically to their fleet and operations.
Have you tried to think if we make some of these trucks a little bit more range and other a little bit less range, how much can we eliminate all the on-route charging just by changing a little bit, even with the same amount of batteries, just better matching?
Yeah, right. Yeah, this is similar to the question about different classes.
Yeah, exactly.
So it gets back to the strategic kind of consideration in terms of what would be the fleet composition, right? Maybe my fleet, I may have some customers that are nearby and then a few customers that are away. So I may have to have two different truck models. That's a different set of customers.
And then maybe we can eliminate most of the charging on route and have only home charge, like base charging.
For the fleet, yes. But another aspect is that many truckers may not be able to afford their own charging station at I wouldn't even call their yard, right? Yeah, many truckers are independent operators, so they still have to rely on some sort of network charging.
So for small owner operators.
Yeah.
In the 3 locations that you have had data, they only have 1 truck.
Right.
So what would you say will be the sweet spot in terms of the battery capacity for the drayage, for the food, and for the other one? But they only can afford one vehicle.
Yeah. So it would be the one that probably they operate the most. They probably have 1 call application that they do, and they probably should gear toward that application. Yeah, size it based on the primary application.
A question from Jonathan. Which model did you use to simulate charging profiles by time of data? Was it the open source NRel Python based model, or did you develop your own model?
So yeah, it's the charging load, right? Yeah, it's our own model. It's based on the activity and the estimated energy requirement from the powertrain model. So we estimate pretty much second by second battery state of charge, and we know like how much the battery is left when the truck arrives back at the point.
Well, I want to thank you, Kanok. Probably in a few days, you'll be able to rewatch the video online. So thanks again for coming.